Hello guys, welcome to this video. My name is Jose. Today we'll be going over double pipe heat exchanger in the Ansys format and software. In our problem today, we will be simulating a heat exchanger involving hot water to heat up ethylene glycol. CFD will give us a better understanding of the interaction. CFD stands for Computational Fluid Dynamics. It's a branch of fluid mechanics that uses numerical analysis and algorithms to solve and analyze problems that involve fluid flows. Computers are used to perform the calculations required to simulate the interaction of liquids and gases with surfaces that are defined by boundary conditions. CFD simulation software is appropriate for fluid flow projects ranging from data research to industries across the world to save costs.
So we're going to open up Fluid, and then we're going to go into the Geometry tab. We're going to select Properties to make sure we're in the 3D format. Once we do that, we're going to go ahead and go back into Geometry, open up to the the Design Modeler. Then once we're in the Design Modeler, we're going to go ahead and make sure the units are an inch. Then we're going to click the XY plane. We're going to get it centered to where we're looking at the X and Y axis. We're going to go in and click Sketch. And we're going to draw a circle. We're going to be drawing two circles to simulate the outer pipe. The diameter for the outer diameter for the pipe is going to be 2.125 inches, and then the diameter of the inner pipe is going to be 2.009. Then we're going to go in and create another sketch. With this sketch, we're going to go and create two other circles for the inner pipe. The outer diameter is going to be 1.375, while the inner diameter of the pipe will be 1.291. We're going to go and rename the sketches for sketch 1 to be outer pipe, and then sketch 2 is going to be inner pipe. We're going to go ahead and do the extrude command for the inner pipe. We're going to add frozen, and then we're going to extrude at a depth of 240 inches. Then we're going to go ahead and also extrude the outer pipe. We're going to add frozen also for that, and then extrude that another also for 240 inches. Then we're going to go and fill, use the fill command so that we can create two solid surfaces, but also create a fluid surface within each pipe. We're going to go ahead and use the Boolean command that's going to help us subtract the bodies, but also preserve them in an attempt to create 4 different surface interactions, 2 solid surfaces and 2 fluid surfaces. If you look, you can see that they're all separated now. Now we're going to go and name each surface just to help with the problem setup. Now we're going to go ahead and do a symmetry cut. This is so that we can have the pipe cut in half on the YZ plane, so that whenever we run our simulation, we'll be able to see the fluid a lot better. So it'll give us a more accurate, well, not more accurate, but just a better result that we can look at and compare, or not compare, and to just see the heat transfer or the heat change. Now we're going to go ahead and click mesh. We're going to set up the meshing outline. We're going to click fine for the relevant center. We're going to click high for the smoothing. Now we're going to click all the bodies. Then we're going to do sizing. We're going to put the element size at 0.003. Now if you look, the mesh is a lot more finer than it was previously once we put a smaller element size, which is going to make the mesh more concentrated, which will give us better results, which is what we need. Now we're going to go ahead and name the selections to help us with when we're setting up the boundary conditions. The inside is going to be named hot inlet. The inner pipe, or the inner fluid, is going to be named hot inlet. The outer fluid is going to be cold outlet. And this is a counterflow problem, so the opposite pipe will say the exact opposite. So it'll be cold inlet for the outer pipe. And then also for the inner, it'll be hot outlet. Then we're going to go ahead and name the outer pipe adiabatic. This is so we can simulate an actual piping system where there will be some kind of insulation on the outer pipe. Now we're going to re-click the inner fluid, and we're going to call that hot fluid. Then we're going to re-click the outer fluid, and we're going to call that cold fluid. Then we're going to name the two pipe sections, as in for the inner pipe, we're going to name it inner pipe, and the outer pipe, we're going to name it outer pipe. And you want to make sure you do a very good setup for your name selections, because whenever you go into your other menu where you're setting up your boundary conditions, it's going to be very useful and very important. Now let's go into setup. These are the options that we use. Now we're in the setup tab. Let it open up. Now we're going to go into models. We're going to turn the energy equation on due to the fact that there's going to be a thermal change between the two different fluids. Temperature is going to be a factor, so you want to turn the energy equation on. Also, viscous model, we're going to do the K epsilon value, the K epsilon. This is just going to give us more equations in an attempt to get a better more accurate simulation. Do enhanced wall treatment also. Now materials, we're going to go ahead in here and select the fluids to be both water and ethylene glycol. This is important because, in order to get an accurate simulation, we want to make sure that we have the correct fluid streams because the properties are downloaded within the software. Now, so for the solid, we're going to go ahead and select copper due to the fact that that's what our two pipes are constructed from. We're going to go into the cell zone conditions. And we're going to assign each fluid its prospective property, or each name is its prospective fluid, and also each pipe its material. After that, we're going to go into the boundary conditions. This is very important because this is basically crucial to how your simulation is going to run. For adiabatic, since there is no heat transfer, we're going to make sure the heat flux is 0. And we're going to make sure, since there's a wall, that it's copper. And then we want to specify for the cold inlet how the fluid's going to attack the pipe. It's going to be normal to the boundary. And we're going to do the type as mass flow inlet in the window previous to this. And then we're going to also change the thermal. This is giving the fluid a temperature setting. Then we're going to go into hot inlet. We're going to do the same thing. We're going to set the mass flow inlet and type, which is the previous window. Then we're going to go in and select the mass flow inlet, and we're going to assign a mass flow rate, make it normal to the boundary, specify the condition in which the fluid is hitting the pipe, and we're going to assign also another temperature. Due to this is a heat transfer problem. Now the software, in order for it to let the two different we use the coupling setting, which will allow the natural heat transfer properties of the two fluids and the pipe interact correctly. So for all these walls, we're going to go ahead and click coupled or coupling, whichever selection comes up. I'm going to go ahead and speed through this just because it's going to be the same. I know y'all don't want to sit here and watch me do it the whole time. And you want to make sure the material is copper for all those selections because it's going to change it. Now you want to do standard initialization. You want to compute from all zones. And after that, you want to click initialize. Then once it's initialized, you want to, we're going to do 50 iterations. Just to speed up the process. Now I got this complete, so we're going to go down into graphics. We're going to do the contours. We're going to go ahead and show you the temperature contour since that's the one of interest. One of interest. And as you can see, the middle part is very red. And then as you go to the other side of the pipe, it begins to turn a little yellow or orange. This shows that the temperature is decreasing, which shows that there is an interaction happening between the solid and the fluid surfaces. The two fluid streams. Then we're going to go into surface integrals. And we're going to do facet average. This is going to give us a average value of the temperature at the outlets. In order to compare to the problem statement. And as you can see in the bottom, the temperature values are located down there. So we'll get a better look at it up top. We're going to have 302 and 363 for the inlets. Now we're going to pull up our MathCAD file, which has our equations already inputted in for this problem. And we're going to go ahead and put in our calculated temperature values from the software for the outlets. And as you can see, once we put the values in, there's only a 2 and 1% difference, which is good. Anything under 5% is very good. And then we also did the problem for parallel flow to demonstrate the accuracy of this setup, which both are still around 2 and 1%. So it's either way, parallel or counterflow is still a very accurate simulation to the problem statement. Hope y'all enjoyed the video. Leave a like and comment, and let us know how we can improve our videos, and there should be more to come.